Welcome to this video on HNMR spectroscopy. Today, we're going to explore the basics of HNMR, why it's essential in chemistry, and most importantly, how to analyze HNMR patterns to understand molecular structures. So, what exactly is HNMR? HNMR, or proton nuclear magnetic resonance, is a powerful technique that allows us to determine the structure of organic compounds by analyzing the behavior of hydrogen atoms, or protons, within a molecule.
Each proton in a molecule experiences a slightly different magnetic environment, depending on the atoms and bonds around it. HNMR helps us map these environments, giving us clues about the structure of a molecule. Before we jump into analyzing HNMR patterns, let's go over a few basic concepts: chemical shifts, coupling constants, and integration.
The first concept is the chemical shift, which tells us about the electron density surrounding a proton. It's measured in parts per million, or ppm, and can give insights into the types of atoms nearby. For example, a proton near an electronegative atom, like oxygen, will appear at a higher ppm. If the ppm value of the chemical shift is relatively small, it is called upfield. Also, the upfield peaks are away from the more electronegative atom. However, the ppm value of the chemical shift is relatively large. It is called downfield. The downfield peaks are always closer to the more electronegative atom. The chemical shift values for each hydrogen atom are provided in parts per million below. Next, there's spin-spin coupling, which describes how protons interact with each other. This interaction creates splitting patterns, such as singlets, doublets, triplets, and more. Each splitting pattern tells us how many neighboring protons there are. When considering the spin-spin coupling, we must find out the n+1 rule in detail. A simple rule exists for predicting the number of peaks expected from coupling in HNMR. Number of peaks equals number of neighboring protons plus 1. These pink-colored H atoms have two neighboring protons. So, the signal is given by pink-colored H atoms split into triplets according to the n+1 rule. Also, these blue-colored H atoms have three neighboring protons. So, the signal is given by blue-colored H atoms split into quartets according to the n+1 rule. Lastly, we have integration. Integration tells us the relative number of protons contributing to a signal. The height or area under each peak shows us how many protons are present in each distinct environment. Tetramethylsilane, TMS, a compound with a signal at the chemical shift value of 0, is usually used in NMR samples as an internal standard. Now that we understand the basics, let's look at how to analyze an HNMR pattern. Start by identifying the number of peaks. Each peak represents a unique chemical environment for protons. Then, check the chemical shift values. Higher shifts often suggest proximity to electronegative atoms, while lower shifts suggest a more shielded environment. Now that we understand the basics, let's look at how to analyze an HNMR pattern. The number of peaks represents the number of the different chemical environments of protons in the molecule. In this HNMR pattern, there are two distinct signals. Therefore, There are two different types of protons in bromoethane. Next, look at the splitting patterns. For example, a doublet indicates one neighboring proton, while a triplet means two neighboring protons, and so on. This information helps us map out which protons are near each other in the molecule. Finally, use the integration values to determine the relative number of protons in each environment. This step is crucial for matching your HNMR data to the molecular formula. Let's look at some examples to apply what we've learned. Let's consider the first example, bromoethane. Now, let's analyze an example spectrum to put all the concepts we've discussed into practice. We will use bromoethane, a simple molecule with the formula C2H5Br. Starting with the structure of bromoethane, it has two distinct types of hydrogen environments. The two hydrogens attached to the carbon bonded to bromine, which we call the CH2 group, and the three hydrogens attached to the other carbon, which forms a CH3 group. Let's look at the chemical shifts of these two groups. The CH2 group, bonded to bromine, appears at a downfield shift, around 3.3 parts per million. This is because bromine, an electronegative atom, pulls electron density away from the CH2 hydrogens, making them deshielded. The CH3 group, attached to ACH2 rather than directly to bromine, is less deshielded and appears upfield, around 1.2 ppm. Next, we examine the splitting patterns for each group based on the N+1 rule. The CH2 group at 3.3 ppm is split into a quartet because it's adjacent to the CH3 group, which has three hydrogens. Using the N+1 rule, where N equals 3, we get 3 plus 1 equals 4 peaks or a quartet. The CH3 group at 1.2 ppm is split into a triplet because it's adjacent to the CH2 group, which has two hydrogens. Following the N+1 rule, where N equals 2, we get 2 plus 1 equals 3 peaks or a triplet. Finally, let's interpret the integration of each peak to determine the relative number of hydrogens. The peak at 3.3 ppm, which corresponds to the CH2 group, integrates to two hydrogens. The peak at 1.2 ppm, which is for the CH3 group, integrates to three hydrogens. These integration values match what we expect for the formula C2H5Br. Let's consider the next example. 1,4-dimethylbenzene has C8H10 formula. Now, we analyze 1,4-dimethylbenzene, a simple molecule with the formula C8H10. Starting with the structure of 1,4-dimethylbenzene, it has two distinct types of hydrogen environments, the 6 hydrogens in the two methyl groups, and the 4 hydrogens attached to the aromatic ring. In a HNMR spectrum, the signals for hydrogen atoms attached to a benzene ring typically appear between 6 and 8.5. In contrast, signals for hydrogen atoms on an sp3 carbon bonded to a benzene ring, benzylic hydrogens, generally range from 2 to 3. Let's examine the splitting patterns for each group based on the N+1 rule. The aromatic H signal is split into a singlet because it doesn't have adjacent hydrogens. Using the N+1 rule, where N equals 0, we get 0 plus 1 equals 1 peak or a singlet. The CH3 group at about 2.2 ppm is split into a singlet because it isn't adjacent to hydrogens. Following the N+1 rule, we get 0 plus 1 equals 1 peak or a singlet. The peak at 7.0 ppm corresponds to the aromatic hydrogen integrated to 1.0. The peak at 2.2 ppm, which is for the CH3 group, integrates 1.5. So, the 1 to 1.5 ratio matches each hydrogen atom. These integration values match what we expect 1,4-dimethylbenzene. Our next example is ethanol. There are three signals around 1.2, 3.7, and 3.9 ppm. Let's label those hydrogen atoms as A, B, and C. The hydrogen atom in the OH group is more dishielded and appears downfield, around 3.9 ppm. The two hydrogen atoms in the CH2 group are also more dishielded and appear downfield, around 3.7 ppm. However, three hydrogen atoms in the methyl group are less dishielded and appear upfield, around 1.2 ppm. Then, we examine the splitting patterns for each group based on the n+1 rule. The signal for the H atom in the OH group named C at 3.9 ppm is split into a single because it's adjacent to the O atom. The CH3 group at 1.2 ppm is split into a triplet because it's adjacent to the CH2 group, which has two hydrogens. The CH2 group at 3.7 ppm is split into a quartet because it's adjacent to the CH3 group, which has three hydrogens. Next, we interpret the integration of each peak to determine the relative number of hydrogens. These integration values match what we expect for ethanol. Thank you for watching, and I hope this video helped you gain a clearer understanding of HNMR analysis. Don't forget to like, subscribe, and share if you found this content helpful.